The next talk in this session will be about mesh messaging for large-scale protests, and our speaker will be Tushar Jois.
All right. Good morning, everyone. My name is Tushar Jois. I'm an assistant professor at the City College of New York and a cryptographer in denial. And I'm here to tell you all about our work on mesh messaging for large-scale protests and why cryptography alone won't save us. So, large-scale protests are increasingly being the ways that everyday citizens can express grievances with their government. For example, in Hong Kong, in Iran, and currently ongoing in neighboring Turkey. And in these scenarios, communication is key to an effective and safe protest. And if I want to communicate with someone, what's going to happen is I'm going to have some kind of cell tower, I'm going to use a messaging app, and send that message to someone else. Now, in an authoritarian regime, of course, the infrastructure can be controlled, right? This centralized infrastructure is owned by someone else, and they can do things like intercept any communication they want, maybe like a Stingray or cell site simulator, or simply by tapping into the cell tower. Now, at the extreme, you may consider that an authoritarian regime will just prevent any communication, straight up shut down the internet, so no one can talk to anyone. So how can we bypass this need for centralized infrastructure? Enter smartphone mesh messaging. Now, this is a pretty simple setup, right? Smartphones are pretty ubiquitous. Urban protests are dense. Send messages from smartphone to smartphone. If I want to talk to someone on the other side of the city, I just bounce it along a path of smartphones, which is pretty intuitive. Now, of course, the authoritarian regime can still monitor this network, but there's no single point of failure in a mesh infrastructure. So there's been a lot of academic work, therefore, on this scenario. So for example, protocols that enhance the anonymity of this setting, protocols that add DDoS resistance and trust, protocols that improve the cryptographic guarantees. And in parallel with all this academic work, there's been some open source work. Started with FireChat and then went on to Bridgeify and Call, but now there are apps that can actually do this mesh messaging thing. So you would expect that this is pretty popular, right? But unfortunately, mesh messaging isn't widely deployed. So our idea was to try to figure out why. So a good way to figure out why is try to figure out what protesters actually need. There's an excellent paper by Albrecht et al. That talked to the Hong Kong 2019 protesters, or at least some of them, to try to figure out what their information security needs were. And they found, among other things, that protesters work in groups, like specifically group chats of about 20 people. So our idea was, okay, well, if we can get better, more efficient group messaging, maybe then we can have a better deployment. So just as a sidebar, like a traditional group messaging scheme, a really easy way to do this is if you want to send a message to 5 people, you send 1, 2, 3, 4, 5 messages, right? So it's essentially linear in the group size. And this works well on the internet. Honestly, we have a lot of internet bandwidth these days. But in a mesh network, you can imagine it's not a lot of bandwidth, right? So a linear in the group size scheme is not going to be as efficient as we would want it to be. Okay, so where do we go from here? Well, we can talk about continuous group key agreement, right? So we talked a little bit about TreeChem in the last talk and how it's the cornerstone of MLS. Well, we used this TreeChem idea to develop a CGK scheme for the mesh case. So as a quick summary of TreeChem and TreeChem-like protocols, you have this kind of ratchet tree where the users are the leaf nodes of a binary tree, going all the way up to a root node. And each node in this tree has a public key and a secret key pair. And each user only has the path to the key material up to the root. So for example, this cyan node here only has these secret keys. Now, but note that everyone has the root's secret keys, right? So if during normal communication, you can use this root in order to communicate with the entire group, right? This is really great because now we're reducing the mesh bandwidth needed, right? We're only sending 1 message instead of 7. And the cool thing about this tree structure is it really lends itself to efficient group state operations. So an important one in this case is revocation from the group. And this is really important in the protest setting. Like suppose that you're this green node here and you realize that your best friend, the yellow node, has been arrested by the regime, right? And we know from prior work that if you are arrested by an authoritarian regime, they're going to download your phone and potentially break all of the secrets. So we have to assume that the phone will be compromised. So what you can do is in this tree setting, you can send 2 state updates to really efficiently eliminate or exclude this yellow node. You can basically say, hey, if I send these two updates and propagate them through the tree, I can make sure that the yellow node no longer has access to secret material in this new root setting. So essentially now we can just communicate using this new root, and we've excluded it. And again, because of the incidences of arrests and protests, having an efficient way to do this is really helpful. Now, I said we adapted it from TreeChem. We didn't just wholesale rip it off. A couple of considerations in the mesh case. For one thing, you need to make sure that you can support out-of-order message delivery, because we don't have centralized infrastructure to enforce order. So we use some ideas from the causal TreeChem line of work to enable concurrency. We also use updatable public key encryption and some related work to provide better forward secrecy and post-compromise security claims. And we also talk about outsider anonymity, because we think that this model fits group mesh messaging much better than the full anonymity of prior work. So our solution is called Amigo. Read our paper for details. The end. No. Because this would be a great talk if this talk was at Ideal World Crypto, because we found something, we solved it using cryptography. We wrote a paper, we put it on ePrint, the end. But we are not at Ideal World Crypto. We are somewhere else. We are at Real World Crypto. And in Real World Crypto, we ask, how can we be sure that it works when deployed in the real world? And this is a hard question to answer, right? Like, it means you throw your micro benchmarks out the window, right? You're not going to just use those for everything. And I also want to point out that we can't get so real world here. Like, we can't go out and start a protest. Could you imagine the IRB you would have to write for that? And then also, just like ethically, like, why would we collect protester data when this is exactly the kind of attack we're trying to prevent? So like prior work, we have to use simulations. But we focus on making them as representative as possible. So this was not easy. It requires answering two questions. The first question is, how do we simulate protester movements? Why do we ask this question? Well, I would argue that modeling node dynamics is really important for talking about mesh behavior. You can imagine that this mesh network, really densely packed, has better routing characteristics than this mesh network, which is more spread out. And when you start to involve mobility, people moving around, it gets even more complicated. So how do we do that in this setting? Well, the Hong Kong 2019 protesters actually wrote a protest manual. They have a good description of all of their protest actions. And this protest is one of the most covered protests in modern memory, a lot of footage. What can we do? Well, we can develop representative mobility models based on this protest manual, based on protester experiences, and based on newsreel footage of the protests. And that's exactly what we did. So here's a still from our urban protest mobility simulator. I'm sorry, it would be animated, but I submit a PDF. Now, you can see here a couple of things, right? This is a city area in a city protest. And we can see there are individual dots that represent people or mesh nodes. And we can see here that there's a march of a densely packed group of people all moving down the city street. And there's also a couple of gatherings here where people are observing a demonstration or a performance of some kind. But I think kind of unique to this case, there's also this notion of a blockade, where people are trying to prevent access to a specific area, for example, by the police. And then there's also this human chain, which I thought was really interesting, of people just passing supplies back and forth. So we use all four of these mobility models, as well as a couple others, in order to develop our experiments. But this leads us to a second question, and maybe the most important question, which is, how do we simulate mesh communication? We have to have an unfortunate detour through networking. So the OSI model has 7 layers. And typically, in secure mesh messaging, people talk about the first 3, right? And it makes sense, because a lot of these papers are talking about cryptography, and they just kind of assume that these lower layers exist, and people have figured it out. Maybe they use Wi-Fi direct, which is pretty common. A couple works claim they use Bluetooth. But these layers are understudied, right? So I'm like, okay, well, we have an opportunity here to do an end-to-end evaluation, right? As I told the PhD student on this, Sarah, let's go in and out, 20-minute adventure. And a 20-minute adventure, it was not. So let's talk about why. The NS3 network simulator is what we picked. It's a discrete event simulator that some of you may have heard of because it is the standard in networks and systems for evaluations. Why? It has really good detailed simulations of each layer of the OSI reference model. So great. What we're going to do is we're going to validate our solution compared to prior work by implementing in the simulator. Sounds easy, right? No. And here's why. Well, first off, NS3 doesn't even support Wi-Fi Direct, which is like what every secure messaging app says it uses, which sucks because we had to spend a bunch of time implementing it on top of ad hoc Wi-Fi. And the second thing is it takes a long time. These are detailed simulations. It took, for one run, 1 week of wall clock time. And I was spending like $500 a day on cloud credits, so this was really burning a hole in my pocket, right? And this is probably why prior work doesn't include high-fidelity simulations of lower network layers, right? It's just simply too hard. But we did it anyway, so what's your excuse? So, what did we learn? We learned that it's kind of a bleak situation. Existing mesh routing just doesn't work well in practice. So let's talk about why. I think a lot of works assume this notion of flooding, which I think makes sense intuitively. If you want to send a message to someone, you just kind of send it to your neighbors in the network, and then their neighbors send it to your neighbors, and ongoing and so on, right? And again, intuitively, it makes sense that your message packets will get there. But in practice, we saw that the message packet delivery rate was about 21%, right? And that's what gives, right? But this is where that lower layer simulation really matters. We basically have message collisions that occur because of the properties of Wi-Fi. At lower layers, you have several nodes broadcasting, their messages collide, inducing congestion, right? So that just results in a 21% packet delivery rate. And interestingly, we found that really well-meaning optimizations don't actually work in practice. So the secure messaging work of Perry et al. Proposes using digests to alleviate some of the problems with flooding. So for example, in this case, maybe you can, if you want to send a message to your neighbor node, instead of just sending the message immediately when you receive it, you can basically say, hey, these are the digests of the messages I have. Basically have some kind of summary. And then your neighbor node can request exactly those messages it doesn't have. So you just send that to them. And the authors claim that it reduces the number of messages, and it indeed reduces the number of message packets sent than in the traditional flooding case. But unfortunately, we only see a 31% packet delivery rate, which is more than the flooding protocol, but I will say it's not nearly as good as we would want it to be. And so why is that? So yeah, we've reduced the number of message packets, but we've added a new packet to the mix. We've added the digest packet, right? So now these digest packets and the message packets are entering the collision domain. So we don't actually see a superlative increase. And this is actually really frustrating because these numbers are much lower than previously assumed. And when you start to add the protester mobility I talked about earlier, things get even worse. As a sidebar, in our paper, we have some information on alternative routing schemes and maybe some new ones that could help alleviate this. So check those out if you want. So what's the takeaway from all this? I gave it away in the title. For mesh messaging in large-scale protests, cryptography alone won't save us. I have an inconvenient truth to share with you all. The relationship between our community and the lower layers of the network stack is this. We have to use simulations. The simulations don't implement the protocols we want to use. When we implement the protocols we want to use, it takes forever and costs a bunch of money, and then the results show that our protocols suck. So it's not exactly a friendly relationship. So what can we do about it? I think there's a clear need for more networks and systems research here, right? We want mesh networking that supports the secure messaging case, right? And I think there's a really cool opportunity here for co-design, right? We have some characteristics from our work about how the mesh network will operate in practice. Maybe that can influence the design of future work in CGKAs. And in the reverse, maybe new cryptographic primitives can help us architect the mesh in a different way. So contact your local systems researcher today. Now, another thing you can do, I think, and I think it's really important, is to try to also figure out from the other angle, the human factors angle, right? I think we talk a lot about Hong Kong, and I talked a lot about Hong Kong. And it's a great example of a large-scale protest, right? But Hong Kong is very unique in that it is a very affluent digital society, right? There are more mobile phone subscriptions in Hong Kong than there are people, right? So it's kind of a unique case. And while work on Hong Kong and Hong Kong protests are super important, right? we can't use it as a blueprint for the rest of the world. And what we need is we need interview studies with more activists from varied geographies. We want to get a broader picture of this whole space. And I also think that what we can do is once we have tools that we think are useful, go back to these activists, do user studies. Because there's this gap between what academics think protests are like and what they're actually like on the ground. And that gap is preventing us from getting usable tools. And yeah, I kind of rag on cryptography a lot here, but I think cryptography is still important. I think with the rise of authoritarianism all around the world, the time is now to really develop the cryptographic systems that can be deployed when and where they are needed, right? We have the tools to provide these security and privacy guarantees that the users need. But as a community, we kind of need to acknowledge that this is going to be an interdisciplinary problem, which means there's going to be an interdisciplinary solution, right? And once we acknowledge that, I think then we can engage in researchers with networking systems, human factors, beyond, for a more holistic approach to this. And I think then we can start a broader conversation about how academics can achieve tangible impact on sensitive populations like protesters. I think only then can we achieve truly practical, efficient, deployable mesh messaging. So that's my talk. I'm Tushar, and my email and website are on there. You can also follow me on Blue Sky. I didn't delete my Twitter, but it's still there. Our paper is available on ePrint, so check it out. Please scan the QR code. We'd love to hear your feedback on it. Also, 2 of the students who worked on this paper are here as well, David and Sarah. So come find us afterward if you want to talk more. Thanks, everyone, for your time.
I have a question about, you have this simulation with a bunch of mesh nodes. How does the adoption rate of the tool influence the effectivity of the delivery of the packets?
Can you repeat the middle part of what you said?
So what if only 10% use this specific app?
I see, adoption, yes. That's a great question. That's actually something we're trying to consider right now. In our prior simulations, we considered everyone was using it. But I think what we want to do is figure out what happens if only a fewer people are using it. And maybe afterwards we can share some of our initial results, and I'm happy to tell you more afterwards. Yeah, thank you.
Hi, Tushar, thanks for the talk. This is a very interesting topic. In Belgrade, Serbia, there was a protest with 500,000 people 3 weeks ago. And the main problem was people didn't know what app to install. So this app that you're talking about needs not only to be available, it needs to be hyper available. It needs to be kind of a go-to thing that a random person in a random country knows that they should install. So I guess my question is, how do we kind of approach that goal to make the app hyper available?
Yeah, that's a fantastic question. And I think one thing that we realized is that we don't have the connections in the community to try to deploy this ourselves. So, we can't go out and just start giving this to people. We're not really integrated in that. So what we've been doing is we've been partnering with people in that space. So I mentioned call.net. It's one of the apps that's used. We actually are working with them to try to see if we can integrate some of our ideas into their system. And I think partnering with open source is actually the best way to go about this, only because, there's more authenticity there. And also it allows us as academics to kind of speak with more technical people who can relay it to the activists on the ground without that technical knowledge, but ongoing.
All right, please join me in thanking our speaker.